In this segment, we're just going to talk a little bit more about a very important topic in reaction rates, because it's something that nature uses, that industry uses all the time. And that is to understand what catalysis is and what catalysts are. And an important thing that you should do is be able to recognize the difference between reaction intermediates and catalysts. At first, sometimes it can be a little confusing because these are both things that are neither in, that don't occur in the net balanced reaction, but are important in intermediate steps. So how do we increase the reaction rate? And so what we need to, a lot of times we want to make something faster, right? We've got a rate determining step. We have some large activation energy, and it's just really slow. We could raise the temperature, but if we raise the temperature too high, it could make things unstable. We want to avoid that if possible. So what we could do is find some way to stabilize the transition state, essentially lower the activation energy. You could think of it as finding an alternate route over the transition state. Introduce some way where it can have a different reaction that has a lower activation energy. So you could think of it this, talking about level and pass before, the bridge, the Einstein, I'm thinking a lot about quantum mechanics, the Eisenhower-Johnson bridge under level and pass, right? We're lowering the activation energy there, and so we can get through much more easily. And so you can see, one way to speed this up is to go to higher temperatures, but another way to speed this up is to make this lower. And that's the goal of a catalysis, to provide an alternate route that has an alternate set of reactions, an alternate mechanism where you have lower activation energies there. And so if the activation energy goes up, obviously the rate goes down. If the activation energy goes down, therefore the rate goes up. And you can see just by plugging into that. So one important thing to remember, the difference between a catalyst and a reaction intermediate, it can be confusing sometimes. So some similarities. So neither of these are found in the net chemical equation. So you're not going to see either intermediates or catalysts in the net chemical equation. However, there's an important difference. You can see if you're looking at the mechanism. A catalyst was there before the reaction started and is still there after all the interactions occur. Whereas a reaction intermediate wasn't there before the reaction started and isn't there at the end. So if you look at the mechanism carefully, you can very easily see, is it something that is present initially? It doesn't have to be in the first step, because it might not be involved till 2 or 3 steps, right? You want to change the rate determining step, so it might not be involved till rate determining step, but it occurs there, and then it is produced again at the end, whereas the reaction intermediate, wasn't there before it is at the end. There's 2 general types of chemical catalysts that are commonly used. One is a homogeneous catalyst, and a homogeneous catalyst would be something that occurs in the reaction that is mixed in the same phase. So, for example, some of the reactions, I think one of the reactions I put up that there's a video of, involves putting hydrogen peroxide in, and hydrogen peroxide acts as a catalyst, but it's mixed in, it's a liquid, it mixes in the solution with everything else. Another common type is a heterogeneous catalyst. It's a heterogeneous catalyst, which you find in heterogeneous catalysis. This is commonly, for example, some metal surface, and then it acts as a catalyst because molecules bind to that surface, and the reaction on the surface has a much lower activation energy. Catalytic converters are an example of this. In catalytic converters, you have a lot of fine particles with platinum, and as it passes over that, then it sticks onto the platinum and reacts, and you get things burning completely instead of being left in intermediates in the burn process. If you have incomplete combustion in a combustion engine, then although the simple reaction may be just to produce carbon dioxide and water, you get a lot of other stuff along the way, and a catalytic converter helps finish that process. So one of the big challenges in heterogeneous catalysis is to find ways to increase the surface area, because it's really the surface area that determines how many reactions are going on. Okay, so homogeneous, the catalyst is in the same phase. The demo that I have online with both catalyst and reaction solution. Heterogeneous, the catalyst is a different phase. automobile catalytic converters. There's lots of other examples in chemical industry processes where you have a heterogeneous catalysis. A common type of catalysis in biology is enzyme catalysis, where proteins act as catalysts for biochemical reactions, and those are generally homogeneous catalysts because the enzymes float around in solution as well. Okay, so a biomolecular one-step reaction has a given interaction energy and a delta of reaction of minus 32 kilojoules per mole at 100 C. By how much would an added catalyst have to drop the activation energy to triple the reaction rate at the same temperature? So we want to triple the reaction rate. How much lower do we need to make this activation energy? Okay, so let's dive in. So we want to be using the Arrhenius equation again. So we have that, no, so we want to be using the Arrhenius equation, but it's not quite the same, right? Because now we have the same temperature and two different reaction energies. So let's go back to the definition of the Arrhenius equation. We have K times A exponential, and we'll call this minus energy activation 1 over RT, right? And then we have another equation, and let's just divide these two. We carry out this reaction with our, in our second situation with a different catalyst, we've got A exponential minus EA2 over RT. So we can look at the ratios of these rate constants, which will just be proportional to these. Now, assuming that the prefactor isn't changed, that's a bit of an assumption, but the prefactors are usually roughly the same order of magnitude for different mechanisms. This would give us exponential EA2 minus EA1 over RT. And so solving for the difference in activation energies, we see that EA, let's write it this way. So take the logarithm of both sides, log of K1 over K2 is going to be equal to EA2 minus EA1 over RT. And so EA2 minus EA1 is equal to RT log K1 over K2. So we can plug this in. This is going to be equal to 0.008314 kilojoules per mole Kelvin. And it's at 100 degrees. So that's going to be 373 Kelvin. 373 Kelvin. And this is going to be log of 1/3. We want it to be faster in K2. And we plug this in, and then we get this is minus 3.4 kilojoules per mole. It's going to be minus because log of any number less than 1 is negative. So we only have to drop the activation energy by about 3.4 kilojoules per mole to make something 3 times faster. So it's, if you can find a catalyst that will give you the same reaction, the same net chemical reaction, but lowers the activation energy moderately, you could really speed in reactions up quite a lot. So a lot of time, this is why biology evolved proteins to do this, to be able to make these reactions happen much faster. And is why in industry, you're always trying to find a good catalyst for the reaction so you can get much higher throughput. Okay, that's the end of this segment of catalysts in chemical reactions.